I'm Freddy Francis and welcome to the laboratory part of our course Introduction to Photonics. So today we are going to see how light is going to get, light as in the laser light is going to get coupled into your optical fiber. So you might have learned in the theory class how the light actually propagates within the fiber. It has this total linear reflection, it takes multiple reflections within this waveguide. Waveguide is optical fiber. It takes its multiple reflections within this waveguide and goes from one end to the other end. So today, in this experiment today, we are going to see how this light, this laser light can be coupled into a optical fiber. So in the course, when you are learning the theory, you might have wondered, right? So how are you going to put this laser light into this small optical fiber? So as you might know, the core diameters, of course you know that the optical fiber is made of the core and the cladding. The core is around 9 to 10 micrometer, 9 micrometer in case of 15 nanometer waveguides. So for a single mode waveguide. So you might have wondered how you are going to put this much of light, this laser light into the small 9 micrometer radius. So in this experiment, we are going to do exactly that. We'll couple light from the laser source into this waveguide, that is optical fiber, and that too we will do for different types of waveguides. As in, we have a here we have a red light laser source. So we will have a few mode fiber here. We have the multi-mode fiber here, and we have a single mode fiber here. So we'll see how light is going to get launched into all of these optical fibers, and then we'll see what is the kind of pattern that is propagated within each of these fibers. We call it what? We call it the modes. So the modes are actually the solutions for Maxwell's equation within a particular medium, and as you have already learned, for a single mode fiber, this is going to be Gaussian shape. And you have already learned what are the solutions for a few mode fiber and a multi-mode fiber. So we are going to see all of these patterns today. We are going to see how light is getting launched, how much light is getting launched, and we will see what is the pattern that you are going to see in a screen when light is getting propagated. So we'll go by introducing you to different components we are going to use today. So as you can see, this is a set of components actually, where we have this laser. This is lasering at 650 nanometer. 650, as we know, is a red laser, and it has around 3 milliwatt of power. It can give 3 milliwatt of power. And here we have a XYZ translation state, and you put your fiber here, somewhere here, and you can collimate. You can actually focus the laser using this convex lens that is coupled. That's already fixed the output of the laser. So what you do is you fire up your laser, you focus the light at the tip of your fiber will come here, and then you make your fine adjustments using this XYZ translation state. So that is the setup. This is actually the entire setup that is required for you to get the laser and focus it onto the optical fiber. Now for making this laser work, you need to give your bias, right? So that bias is being provided by this kit here. So we call it the laser driver. So what the laser driver does is it gives a constant current at the input of the laser, so that while you increase the current, the laser will increase in its intensity, and you will get a more intense beam. Now as you can see here, we have a small symbolistic circuit diagram that is given. This is the bias voltage. We have a resistor here, and another potentiometer resistor R2 here, and we have the laser diode that is being connected through this particular pin. So you have to connect it here like this. You don't need to consider this part of the circuit. So what happens here is you give the bias here, and then you change your resistance using this knob, the potentiometer knob, and this will increase the current through this laser diode, which is actually passed into this here, and you will see that more the light flow or light intensity increases as you increase the current flow just after the threshold. So as you know, laser is a thresholding device, so it stays off, or it will laser with very little amplitude until it turns on beyond a particular threshold current. So you'll be able to see that until that threshold current is reached by rotating this particular knob, only spontaneous emissions will be there, only a small amount of light will be visible here. Once you cross the threshold, you'll be able to find that the intensity changes very rapidly. So all of these things will be demonstrated as we turn on these instruments. Now this is the source part. We actually will be coupling the light into the optical fiber. We have 3 different optical fibers here. So so as you can see, these are 3 or actually 4 of them are there. So these are color coded. Okay, so I'll start with the one having the maximum core radius. This is the orange fiber. This is multi-mode at 650 nanometer. As you can say, a fiber cannot be specified to be multi-mode or single mode. Just generically, it is wavelength specific. Of course, because of the mode matching conditions. Now, this orange fiber is multi-mode for our 650 nanometer laser here, and it has a core diameter of around 60 micrometer. Now we have another fiber here. This is a plastic fiber which is having much bigger core dia. So it is again multi-mode for 650, and we have our commercial 1550 optical fiber here. So this fiber is having cutoff of a wavelength at 1260. So this is single mode at 1550, our communication wavelength. But in this experiment, we are using a 650 nanometer laser source, which is this. So this commercial optical fiber is going to be few moded. Commercial single mode fiber is going to be few moded at this particular wavelength. So I reiterate again, a fiber can be single mode only at a particular frequency, or only beyond a particular wavelength. So this fiber is single mode beyond 1260. So we are using a 650 nanometer laser, so it's going to be a few moded optical fiber for our particular application. So we are going to use this fiber as a few mode fiber. Now we see the single mode fiber at 650. This is a single mode fiber 650. This is having a core diameter around 3 micrometer. So you can see the difference, right? This is 60, this is 9 micrometer, and this is just 3 micrometer. At this 3 micrometer, this optical fiber is actually going to be single mode for your 650 nanometer laser. Now that's the fibers that is covered. We'll move into the detectors. So here we have the detectors. I'll just take this aside. So actually the fiber tip will come here, and it will launch the laser into this rotation stage. And in this metallic part, so you can see the photodetector here. So it is actually a slightly big photodetector. So and you're going to use it in a free space kind of application. So you'll be launching light from this part. Light will fall on this, and you can actually rotate this around. Now you will be wondering why we have to rotate this setup. This is one thing we are going to do as a part of the experiment. We are going to measure the numerical aperture of the optical fiber. So specifically, we are going to measure the numerical aperture of this particular optical fiber, which is a single mode optical fiber at 650. So we are going to do the numerical aperture measurement of this particular fiber. This is single mode fiber at 650 nanometer. Now what is numerical aperture? Numerical aperture can be thought of as a cone like this, within which the light has to fall so as to get coupled into this particular fiber. Okay, so any light that is within this fiber, within this cone of numerical aperture, will be able to get coupled into this particular fiber, and any light that is outside it won't satisfy the critical angle within the fiber and will not get coupled into the fiber. So in this as a part of this experiment, we are going to find the numerical aperture for this particular fiber also. So numerical aperture is actually the sine of this acceptance angle. Okay, sine theta is the numerical aperture. You're just going to put this here, and then you can then the light will be launched here, and then you can measure the mode intensities by rotating this. Now we have the sources there. So this is a photodetector, and this photodetector converts your optical energy into electrical energy, and this electrical signal is being passed through this cable towards this segment, which actually gives a measure of how much the values are. I'm just going to connect this up now. You have to switch it on here, and as you can see, it is having around minus 19 dBm of output that is being displayed here. This is because of the ambient light that is present here. As you can see, this is a pretty bright set, and then all the light energy is going to get detected by this particular detector, which is working at the visible spectrum. Now, so as you can notice, minus 19 is pretty high a value for our experiment. We will get to know when we start the experiment. So the problem here is, unless we remove the ambient light, we won't be able to detect how much power is actually being emitted and coupled into the optical fiber. We are going to keep the setup in a darker facility and we'll measure it. So you will find that most of the results we are going to see is going to be in a dark background. So we have another photodetector here. So only difference with the other photodetector is that it is the detection element. The photodetector part was in another place. In here we have something integrated here. I'll show you this. This is the photodetector. You can see that is below there, and here we have this connector, so that we can connect or we can easily couple this optical fiber to this particular connector. So now we'll connect this back. We are going to turn on this laser. We are going to attach this fiber here, other end here, and see the power. So for all the optical fiber based experiments, it's actually a very good practice that you clean your fiber tips. So what you do is, you have your cleaning paper here. So you rub it 3 or 4 times in the same direction. Lift, rub, lift, rub again, like this, in different spots of the paper. And then once you feel that one section is slightly dirty, you pull it like this and then keep doing that. So that's how you ensure the fiber tips are actually devoid of any dust. Now you connect it here. There's a notch here which has to match. So we have our connection set here. So we have a free space link here. The light travels in the free space here, and we have the optical fiber here, and then which is connected to the detector. Now we'll turn on this particular laser driver. You have a switch behind. You won't be able to see that. I'm turning it on here. The LED indicator turns on, and here now the potentiometer is the highest resistance region. I'm going to decrease this resistance so that the current flow increases and more current flows to the laser, and see how the intensity changes. As you can see, small red dot is actually visible. I don't know whether it is visible for you guys. So small red dot is visible, and I'm going to increase the current. The laser having turned on it is still a very small pattern, small speck there. Now you can see the light is slightly increasing, but you can see that the light is slightly increasing and then suddenly turns on. This is where the threshold is, and the laser has turned on, and beyond which I don't have much to rotate here in the multi-port potentiometer. But as you might have already noticed, the pattern I'm seeing here is not that great a pattern. It's like a line, right? So that means that laser is not focused at that point. So to rotate this particular lens, the convex lens, so that you get a small spot. You have to make this spot as small as possible. But as you try to do that, you see that laser is so bright that you won't be able to clearly say whether the spot is really small or not. For that, what you do is you reduce the intensity slightly. Now that the spot is less bright, it will be easy for you to discern whether the spot is falling on the optical fiber or not. So I have pushed the fiber there, and now I can see the spot pretty easily. I can see the spot now without hurting my eyes also. Now I have to adjust this lens so that I get the sharpest spot possible, which will mean that all the laser light is focused on that particular spot. And once you can make the spot fall within the numerical pressure of the fiber, light should get coupled into the fiber. So that's what you are going to do. So I have put it in here. I will try to increase the current now and see the measurements in this photodiode. So as you can see, not much light is actually getting coupled here. I'll keep increasing it. Now the laser turned on. Still almost nothing is coming here. Now that we have focused most of our energy in the spot, our idea should be to make that spot fall at the dead center of the optical fiber, so that all the energy is coupled into the optical fiber. So for that we use the XYZ translation stage here. You move it around a bit, see how the values changes in here. So as you can see, it's already started to change. Minus 48, 36, 26 is 25, minus 25, 21, 19. It's getting better. Minus 14, minus 30. So yeah, we have gone away from it. So this is the real painstaking part of the experiment. You really need to be careful and patient with aligning your setup. So yeah, so around minus 12 to 13 is what we are able to couple into this particular optical fiber. Now, as I told, this is a multi-moded optical fiber for 650 nanometer laser. We are going to try and change this optical fiber, replace it with something which is having still better, still bigger core diameter. So this is the black plastic optical fibers. This having much higher core diameter than this orange fiber. You just see how much extra power it is able to couple into the optical fiber. So for that we had to reduce the intensity to minimum, replace the fiber, and maximum power it is able to couple almost minus 5 dBm of power. So that means that the bigger the core diameter, you are able to couple much more light into this optical fiber compared to the other orange optical fiber. Now that is coupling into multi-mode fiber. We'll try and couple light into the few mode fibers now. We'll try, this is the few mode fiber. So we'll try to couple light into the few mode fiber, and we are going to find it a bit more troublesome to get enough power into this particular fiber. So again the procedure is the same. You can see by default it is coupling only minus 26 dBm of power, minus 27, right? 27 dBm of power. So what does that mean? That means that with the same setup, okay, we have used the same, I haven't touched the XYZ translation stage, only less power is getting coupled to this particular fiber. Now that is because probably the alignment of the other fiber was not that good, and it was not that mandatory for the fiber to have that good an alignment. In here the fiber needs to be coupled very properly with the optical source, so the light should go in. Now we had to do some fine tuning so as to get maximum power out into this optical fiber. So again you had to do some XYZ translation. So as you can see, with great difficulty we are able to get around 18-19 dB of power here. So that's how you couple light into the few mode fiber. So again we'll repeat the same with single mode fiber. So single mode fiber coupling light should be slightly more complicated than this, because as you know the core dia is again just 3 micrometers. So you are going to focus your light through a free space setup into a 3 micrometer small optical fiber. So this is going to be challenging again. So but now we have something working in our favor, is that we have already set up this XYZ translation stage on the lenses such that almost a rough alignment is there. So we'll see just by plugging in the single mode optical fiber here, let's see how much power you are able to get. Yeah, we are able to couple minus 32 dB, minus 27, 28, 29, yeah, around minus 20 something dB we are able to couple roughly. Okay, so with a bit more of alignment here, we'll see how much we are able to couple actually into this fiber. So just again we'll try to, so now you can see you are able to couple almost minus 25 dB of power into the single mode fiber. You can see the slight losses in here and all. Now so that's it. So we have coupled laser light through this free space setup into the optical fibers. Now we are going to see how the mode pattern looks inside this fiber. So mode pattern again is a pattern by which the light propagates within the fiber. It's actually the solution for the Maxwell equation within the fiber. Now we'll see for multimode. You know that there will be going to be multiple blobs of light intensities, and for single mode it's going to be a smooth Gaussian curve. And for the multimode fiber, you're going to see a speckle pattern. Speckle pattern is like random. You'll have a lot of optical modes, and you'll see just a speckle pattern. So we'll try to visualize these things onto a screen or something, and we'll study the modes for each of these fiber. So yeah, now you have coupled the light into the multimode fiber, and here you can see the pattern. So this is what we call the speckle pattern. So speckle pattern is the interference of different modes, and you can see different modes. Modes will change. Those modes will change once you start playing around with the fiber. So you bend the fiber slightly, you see that the interference patterns changes. That is because the path they take will need to change. So now I am going to bend the fiber a bit, and you can see the pattern will change on the screen. But there is another thing you have to notice, is that as you keep bending the fiber, the light start getting lost, escape from this bend. So the more the light escapes, you will be able to see more of a glow here. So now what happens here is that as you bend the fiber, it becomes more difficult for light to get total internally reflected from this bend. So as you decrease the bend radius, more and more light is escaping from the core to the cladding. We have connected the few mode fiber, and we got really lucky that we got a LP02 pattern pretty intact here. So as you can see, the ring structure is pretty intact there. You can see the center maxima, a darker ring, and then a brighter ring. So that is LP02 mode for you, which we obtained using the few mode fiber. And now I am going to demonstrate something. I am going to bend the fiber, and you can see that the pattern changes, and suddenly becomes the fundamental mode, LP01. So this is because the higher order modes, we tend to say that the higher order mode travels closer to the cladding, and when you start bending it, higher order modes are the ones which escape from the core the first. So as you can see, now you have the mode back. LP02 mode is back. Now if you again bend it, you will find that it will escape from the core, and you will have only the fundamental mode that is coming out there. So if you keep on bending the fiber, you should be able to excite other modes also. As you might be able to see some other modes coming in and going out. So it's actually very difficult to excite a particular mode of a fiber. So you can see probably like mix of 2 or 3 modes in here. So it's mostly LP02 mode that is coming and going, and then you will be able to see some other modes also if you just play around the launching conditions a bit. See, you can see some other pattern now. So these are all interference of multiple modes. So this is using a few mode fiber, and again if you bend the fiber, you should be able to see only the fundamental mode that is coming out, and you should be able to see the light that is escaping from the cladding as a glow, as we did in the last experiment. So this is multi-mode fiber for you. This is few mode fiber for you actually. This is few mode fiber for you. So now replace the few mode fiber with a single mode fiber. Now as you can see, the intensity, the brightness of the spot is much fainter. That is because we are not able to couple that much of light into the single mode fiber, as we have noticed before. Now you can see that the pattern, I'll bring the thing a bit more closer for you to understand. So as you can see, the pattern is much more it's a single pattern, and yeah, this is a Gaussian shaped pattern. So you can see that maximum intensity is at the center, and then it gradually fades away to the edges. Now this is the LP01 mode, and the only mode that is being propagating the fiber, and we call it the fundamental mode. So that is using the single mode fiber. So again, if you bend the fiber, there's nothing much to see actually. You'll have a fainter pattern of this LP01 mode. So how so much ever you bend, you'll still be able to get this fundamental mode out of the fiber. So now that we are done with coupling the light into the fiber and seeing which all modes are propagated in the fiber, we'll go straight in and do something different. We're going to find the numerical aperture of an optical fiber. So we are going to use the single mode fiber, which we have told like 3 micrometer is the core radius. So we are going to launch light into this 3 micrometer optical fiber and see up to what angle the fiber can absorb the incoming light. So we call it the acceptance angle, and sign of acceptance angle is the numerical aperture. The acceptance is actually treated equivalent to the light that is coming out of it. So what we are going to do is we are going to see the light output profile. For that we have a rotation stage here, which is mounted with a photodiode. It's a remote photodiode. It actually converts the optical energy to electrical energy and then transfer to this wire to this display here. So as you can intuitively guess, I have coupled the laser to this optical fiber here, and the other end of the fiber is connected here. Now this fiber is launching in light in this direction. In this particular cone it will come. I am going to scan across this particular light cone using this photodetector. Okay, you are going to scan it like this. Okay, so and then you are going to measure the value in this display and then plot it. You plot it, and what you do is you will get a Gaussian curve like this. As you know, the mode profile of the single mode fiber is a Gaussian curve. You will get a Gaussian curve like this. Okay, so from this particular Gaussian curve, there is 2 measurements we can take. One is the mode field diameter can be found from this. So mode field diameter is found when you take the 13.5% of the maximum. You find the full width half maximum at that, and you put that in a particular equation, and then you get the MFD. And for finding numerical aperture, instead of 13.5, you go for the 5% value. So at 5%, what is the full width half maximum? So sign of that is going to be your numerical aperture. So you are going to get something like this. The curve is going to look something like this, and then at 13.5, okay, that is 1 by e square. That value is 1 by e square. That is the significance of the value. You are going to get the MFD. This is WW, and this is the mode field diameter. And if you go for the 15 or 5% in each side, that is going to be further below like this. You are going to get the numerical aperture. Numerical aperture is sign of that particular angle. So you might have noticed that here it is angle in our case, and then here it is intensity. So yeah, so that's it for the week. So we have done with our experiment on launching our laser light into the optical fiber, and what all things we have learned? We have learned that it is much more easier to couple light into the bigger fibers, that is the multi-mode fiber followed by few mode fiber followed by the single mode fiber. So it was really easy to couple light into the multi-mode fiber, and we got very good optical power output of that, which was slightly less for the few mode fiber, and we actually could see the few modes, and then we coupled light into single mode fiber with a bit of difficulty, which was again found to be relatively lower than that of the few mode fiber. Now we moved on from coupling light into actually seeing the modes, and we found that for the multi-mode fiber we have a speckle pattern in which we can't really clearly see the different modes, but instead we have a pattern which is the interference of different modes. And then we moved. Then we used our few mode fiber. There we got lucky and we could see the LP02 mode along with few other modes when we bent the fiber. And when we bent it sufficiently enough, we could see that the other modes get eliminated and just the fundamental mode was left out. And in the final part, we could couple light into the single mode fiber and see the corresponding mode profile, which is the LP01 mode, which is a Gaussian shaped one. So that was about coupling light and seeing the modes. And in the final part of the experiment, we measured the numerical aperture and mode field diameter of a single mode fiber by rotating a particular photodetector across the mode profile of the single mode fiber, and we could find the corresponding values of numerical aperture and mode field diameter. So I hope this was an enlightening session for you guys, and I hope this gave much more light into your visualization of the theory which you have learned in the class. So thanks a lot for watching.